and you'd get instant kernel code execution. So nobody would be silly enough to make that mistake. But as we already know, CS loses its magic value in virtual 86 mode because you need to be able to access these this 20-bit real address space. So it's completely reasonable to request any value. But we still need to cause IRET to GP. And we did this by setting the TF flag in the E flags image when returning. So Intel actually considers this sensitive and hardens control over the virtual 8086 mode monitor. But this is actually poorly documented. And in fact, there's no mention of this at all in the documentation. And from research, we know that early versions of the Pentium processor would in fact not treat E flags, TF set in the E flags image as sensitive. And that wasn't considered sensitive at all. But apparently, during some later revisions of the Pentium, Intel updated this and did consider it sensitive. And in fact, this is really documented by, I don't remember his name, the Sandpile. Yeah, so there's this great resource online called Sandpile where lots of crazy Intel tricks are documented. And yeah, so it's explained that at some point Intel decided that this should be sensitive and they updated it. But they never issued any errata or they never updated any documentation. So what we think might have happened was that Microsoft, during this, when Microsoft implemented this, they believed that they could rely on this. And then Intel suddenly changed the x86 document specification so that it was sensitive, and Microsoft never bothered to check whether these checks were still valid, which is pretty reasonable. I mean, how many people check this low-level code every day? It's the kind of thing that you write once and nobody remembers how it works. Just don't touch it. So yeah, so we found that by experimentation we proved that this is actually still the case. So I have a video of this. It's not particularly exciting to watch, but it's. Okay, so yeah, so I wrote a reliable exploit for every supported version of Windows NT. You basically just invoked a new process and it would hand it over a system token. So yeah, it was very reliable and it worked perfectly. And in fact, it was a bit of a challenge to write because all the existing published shellcode for Windows NT privilege escalation bugs were never expected anything to work across more than one or two kernel versions. So everything published was like very Windows XP specific or whatever, and they had like hard-coded offsets into structures and so on. And so yeah, I spent some time working on a completely kernel-neutral version that would work on every version of Windows NT, simply because there wasn't an exploit no exploit existed like this around that I could reference. So I have some code that I can show you. So what I did was, so this is where where the kernel lands after I exploit this vulnerability. And so basically I have to start writing a driver code as if I was writing a real driver based on like, symbols that Microsoft supports, so that I could be sure that they would be available on every kernel version. So yeah, I basically have to work out where my kernel is loaded and then start passing the kernel exploit directory myself manually. So then I can basically write driver code as if I was writing a genuine driver. So because the kernel stack gets desynchronized because I'm passing it this fake stack that I wanted it to swap to, it turns out that my whole K-thread structure gets completely messed up. And in order for this corruption to propagate to other parts of the system, I have to repair it. So I find all references to this fake stack I've set up and restore them. Because I'm going to kill this process anyway, because I only want it to use it to paste a privilege token onto another process. I don't really care what it points at. I just want it not to be corrupt anything. So yeah, so basically, yeah, I search for all these values. Then I find the most privileged process on the system, which is the initial system process. Grab a reference to its primary token and then paste it onto my token. Paste it onto this process that's unprivileged. And yeah, and this works on. This only uses exported symbols that Microsoft support for driver developers. So it's completely reliable across every NT version that was affected. So let's see. So basically, yeah, I set up this kernel stack, and the offsets for things like restoring the TEB and the new stack pointer, which is going to be a fake stack in the user address space, and change the return address into my exploit. My payload. So you need, in order to access this code, you need a data structure called a tib in your tab. I don't know what TIB stands for. I guess it's thread information block or something like that. But TEB is obviously thread environment block. Then you initialize the VDM subsystem, and it turns out because this data structure is unsupported and undocumented, Microsoft don't mind changing it as much as they like, which is obviously completely reasonable. But in order to identify which version is being used, there's a size field, which if it isn't the correct value, they say they return access denied. But because I don't know what the size should be, because in fact it even changes between service packs, so I can't even guess from the version. So I just basically have to brute force it and try every value until it works, and this works fine. So yeah. Because the real address, virtual 806 mode, Intel expects you to map the virtual, the fake real mode address space on the first page. You need to map null, the first page. So there's no documented way to do this, and in fact, if you try to do it with any of the Win32 APIs, it just doesn't work because null has special meaning, and it means you have no preference to whether this is going to be mapped. But if you use NT allocate virtual memory, which is the system call that backs all the stuff that all the regular allocation stuff like virtual alloc and so on, then it's possible to do that because it rounds down addresses to the nearest page. So if you wanted something mapped at 1, the address 1, then obviously 1 isn't a page boundary. So if you want something mapped at 1, the only way to do it is map something at the next available page, which is 0. So yeah, you basically just pass in a really low address, it rounds it down to the nearest page, and you get it mapped. And there you go, and that works. So we've also been working on automation and fuzzing for operating system kernels. So we've been working on system call exploration to try and find interesting attack surface that we want to reach. On Windows, the system call interface, it's complex, it's unstable, it's unsupported, and it's undocumented, and it's also pretty vast. If you consider Linux has about 300 system calls, Windows actually has about 1,400. But in fact, that's a pretty conservative value because Microsoft really liked this design of multiplexing system calls. On Linux, there's only one multiplexing system call, which is socket call. So things like bind, accept, send, and things like this are all the same system call called socket call, and you just pass a value saying which one you wanted. But Microsoft love this, and they have dozens and dozens of them. So you pass a magic value which tells them which system call you actually wanted, and it can be dozens available via one entry point. So in fact, 1,400 is probably a pretty conservative value. There's basically 1,400 SSDT entries, but there's more likely, I would guess, about 3,000 system calls really. So on Windows, these are designed only to only ever be called by Microsoft code. They make it very difficult to call system calls, and they're not supported across versions. So they don't mind breaking stuff, which is perfectly reasonable. This is all expected. As most people know, I guess they randomize system calls for system call numbers between service packs just to make sure that you're not trying to rely on this. Well, I guess that's probably not what it's designed to do. They just do that as part of the build process, but that's the effect. Because no Windows programmers call these system calls directly, they only go through the Win32 supported and documented APIs. They're rarely exposed to malformed parameters. So in general, simple fuzzing can still expose interesting bugs, simply because real-world programmers aren't touching this stuff. So yeah, on Linux, if it's expected that just regular programmers will call system calls, and in fact, when new system call functionality is added to Linux, it's quite common to see regular programmers post bugs or reports that an oops has been caused as they try out the new code, and this weeds out lots of bugs before it reaches anything that could be security sensitive in like enterprise distributions or whatever. But yeah, this isn't the case on Windows simply because this isn't designed to be called by end users. But obviously there's nothing stopping you to actually do that if you're an attacker. So also the design of system calls on Windows NT is very different from the philosophy on Linux. In general, on Linux, structures are very simple. They can be read in 1 or 2 operations, and they're easy to pass. They're very simple structures, but on Windows, they're often complex objects. They're multiple levels deep. They have large interdependencies that all need to be passed. If you set pathological parameters in these complex structures, you can reach some very rarely exercised code. And in fact, there's code that you just simply cannot reach via any supported interface, and it's difficult to imagine how Microsoft managed to test this. And no end users are going to complain simply because they'd never rely on this code. Of course, kernels also pass lots of interesting stuff like fonts and other complex formats, and this is all done at Ring0, and these are great fuzz candidates. So we've been working on system call fuzzing. So trivial fuzzing can still find Windows bugs. The attack surface is really large, and there's lots of system calls to play with. You can find fuzzing on Linux, but in general the task is not so trivial simply because the interfaces are so simple. It's tough to get them wrong. You need to do some work. You need to set up some I don't know, complex state with file descriptors or whatever. But fuzzing will find bugs, and we've had some success this way. We've been developing some techniques for working on this that we're trying to integrate into things like Chrome OS release. So we're hoping that this can help make things like Linux privilege escalation via malformed system call operations easier to spot as they're introduced via regression testing and so on. So we're hoping this is going to help Linux local security in future. So yeah, now we're going to talk about protecting the kernel from malicious LAN code.
One of the first ways that was quite popular to try and protect the kernel from malicious user-land code was just having trusted path executables. So, well, I mean, the idea is just to have trusted executables only. So it's reasonably old. I think I've seen this. I've seen people running shell boxes in the mid-90s using this. So it was pretty popular, and there was a very naive way of doing it on Linux, which was to just mount all use of writable paths to no exec. So if you could write somewhere, you could not execute the code. There were trivial bypass for this. For instance, for systems which already supported dynamic libraries, at the time, you could just go through the dynamic loader, because the dynamic loader LD would be in a trusted path, and it would happily map your code. It's a job, and execute your code. GR Security had a good GID UID based one for years. I think it was released in 2000 or something like this. And nowadays, it would actually work if you, well, it could almost work if you would just mount something with no exec, because nowadays the semantic is actually respected, and it does prevent file mapping as protexec and not only execv. So this approach is gaining some popularity on the Windows platforms through whitelisting. We've seen a few products that try and perform whitelisting on the Windows platform. So the idea is just to prevent gaining arbitrary code execution in the first place, so that you can't attack the kernel. But of course, there are tons of ways to bypass this, because arbitrary code execution should not only mean arbitrary opcodes. You can exploit lots of kernel bugs from a Python or a Ruby interpreter. So if Python or Ruby are in your trusted path, you can just exploit kernel bugs through this. Also, if you think about powerful executables such as GDB, you can do whatever you want through GDB. So if you have access to GDB, you can obviously run arbitrary code. Also, quite interesting tweak if you're trying to build a system with trusted path executable, the threat model is completely changed for many binaries. For instance, a local vulnerability in NetHack or the Minesweeper on Windows would become useful, because they would allow you to run arbitrary code. And you've probably seen a few releases, such as vulnerabilities in make or vulnerability in ZSH, which didn't really make any sense. But in this very paradigm, they do make sense. So, of course,